All right, let's take a look at Lesson 9, Variability in Samples from Unit 7. And so we are going to explore how samples can be different. So we're going to look at calculating means and sample proportions to estimate population means and sample proportions. Okay, so in 9.1, selecting samples, coins are usually stamped with the year and location of the mint where they are made. D represents the mint in Denver, Colorado, and a blank or P represents the mint in Philadelphia, Pennsylvania. Diego has a jar containing 36 coins. Select a sample of 5 coins by rolling your number cube once to represent the row, and then rolling again to find the column. So for example, rolling a 3 and then a 5 would represent selecting the coin marked 2000p because we're using this table here. So we said 3 and then 5, so row 3, column 5, that's 2000p. All right, so we are going to do this process to collect a sample of 5 coins. So again, the first roll is the row, the second roll is the column. All right, so we're going to use this template, or I'm sorry, this applet on the right-hand side since we don't have enough dice. So we're going to roll. So we're looking at row 6, column 5. So we have that one. Then we have row 6, column 3, row 3, column 1, row 6, column 3, we already have that one, row 6, column 2, and we need one more, row 4, column 2. All right, so there we have our values. And so we are recording our values. Those are really small, but that's okay. So we had 2012D. And I don't remember, let's see, okay, it doesn't give me that. I don't remember the order that we found them, but that's okay. Let's see, we had 2009D. We had 2005P. And 2017P. And 2012D. All right. Okay, so we can find the sample, or the mean of the sample. And so let's do that. Let's see. We're going to do a new window, and we're going to use, I thought I had, oh, no, that's not that. All right, so we'll just type in Desmos for a calculator. We'll just use scientific. All right, so we have 2012 plus 2009 plus 2005 plus 2017 plus 2012. And then we're going to divide that by 5. So 2011 is our sample mean, not 2001, 2011. All right, and then the sample proportion minted in Denver. So we had 3 out of the 5, so 0.6. So 60% of them were printed in Denver. All right, so now let's go back to our applet there, and we'll do the next roll. All right. So we're gonna, oh, that's just 2 copies of the same thing. All right, so now we're going to do Well, we can do it this way. All right, so we're going to roll. That's our row 6, column 4, row 6, column 4, already did that one, row 5, column 6, row 4, column 5, row 3, column 3, and we need one more. Row 4, column 4. All right, so now we're going to record those. So we had 2001 D, and again, it doesn't matter the order that we write them down. 2014 D, 2013 P, 2014 D, and 2015 D. All right, and then we're gonna go back to our calculator there, tap those 3 dots. Oh, nope, there's my calculator. All right, and then we're gonna clear all. All right, so then we're gonna do 2001 plus 2014 plus 2013 plus 2014 again, plus 2015, and then we're going to divide that answer by 5. So we get 2011.4. Oh, I keep doing that. 2011.4, and then this time we had 4 out of the 5 were in Denver. So that was an 80% chance. All right, so now we're going to do the last one. So let's switch back to our applet. Nah, that's not what I meant to do. All right. We're going to switch back because that will drive me crazy. All right, and there's our applet. Okay, so let's do this one more time. So we're going to roll. Actually, let's just reset the whole thing. All right, roll. And our row is 6. And our column is 4. Row is 1. Column is 3. The row is 1. Column is 1. Row is 5. Column is 5. We need one more. Our row is 3. And our column is 4. So 3, 4. There we go. All right, so now we have all of the ones that we need. So we'll do 2016 D. And then we had another 2016 D. Then we had 2001 P. Then we had 2013 P. And then we had 2004 P. All right, so now we don't need that applet anymore, but we do need our calculator. We'll clear all that. All right, so we have 2016 plus 2016 plus 2001 plus 2013 plus 2004. All right, and then we're going to take that answer and divide by 5. So we get 2010. And then how many of those were Denver? It was 2 out of 5, which is 0.4. You can use a calculator for that if you need to. All right, so for sample 1, there was a 60% chance, or 60% of them in that sample were from Denver. And the mean year was 2011. Sample 2, the mean year was 2011.4. And then there was an 80%, or 80% of them were minted in Denver. And then in sample 3, the mean year was 2010, and 40% of them were printed in Denver. All right. Okay, so Not all the samples have the same mean and proportion. Why do you think that is? Well, remember that it's random, right? They are random samples. So each sample has a chance of getting different coins. So if we were to look at a histogram for this, we would notice that it would be a normal distribution. In the interest of time, we're not going to go through all of that. Plus, we need samples from the entire class. And so we would find some other interesting things going on there. We would have... well, yeah. All right. So in the interest of time, we'll just skip to 9.3. Variability of sample estimates. A political campaign sends volunteers out into various parts of the state to get a sense of how well their candidate will do in an upcoming election. 30 volunteers each get a random sample of 10 people in the state and find the proportion of people who are expecting to vote for their candidate. The sample proportions are summarized in the histogram, and they already tell us that the mean of these sample proportions is 0.55, and the standard deviation is 0.15. So out of all of those samples, right, the mean of those samples is that 55% of the voters in each of the samples will vote for that candidate. And then the standard deviation was 0.15. All right, so recall that for normally distributed data, about 95% of the data is within 2 standard deviations of the mean. What percentage of sample proportions are within 2 standard deviations of the mean for this data? All right, so our mean is 0.55. which would be right here. And then a standard deviation is 0.15. So if we have 2 of those, then it's 0.3. So we're going from 0.55 up to 0.85, which would be right here. And we're going down to 0.25, which would be right there. Okay, so that would be 2 standard deviations. Now, if you're looking at the bars, you might want to look at the interval from 0.2 to 0.3, since we're in the middle of the bar. So let's go ahead and take a look at it that way. So if we were going from here to here, how many are there? So we have 1 on that bar, 4 on that bar, 6, 8, 6, and 4. So we have, let's see, 28, 29. So if we go from 0.2 to 0.9, we have 29. If we went from 0.2 to 0.25 to 0.85, it would be around 28, because you're not going to count that 1 bar. So let's just go with, if we went from 0.2 to 0.9, right, and then, so we had 29 out of, oh, I still have my eraser, of 30, right? And so 29 out of 30, oops, is about 97%. And that does match, 97 is just a little bit more than 95%. So that is approximately normal. All right, and then estimates for population characteristics are usually given along with a margin of error. The margin of error is the maximum expected difference between the estimate of the population characteristic, which is the mean, and the actual population characteristic. So what do we think that population characteristic is? And in this case, we're talking about the mean. So our sample mean, what's the difference between that and the actual population mean? So each of the sample proportions are good estimates of the population proportion. Actually, these are sample proportions, not means, sorry. So we should give a margin of error that contains about 95% of the sample proportions to be reasonably sure that the actual population proportion is in the range between the mean minus the margin of error to the mean plus the margin of error. What margin of error should be given along with the estimate of 0.55 for the population proportion? Okay, so what the heck does that mean? All right, that means that if we're looking at 95% of the data, we know we want to be within 2 standard deviations. Okay, so if we found our sample proportion, the mean of the sample proportions was 0.55, whoa, then we're looking at 0.55 minus 2 standard deviations, which we already found was 0.3, because we did that up here when we were looking at the standard deviations being 0.15. That's 1 standard deviation, right? So the lower limit is minus the 0.3. The upper limit is plus the 0.3. And you always have, if you add those two numbers together and divide by 2, you should always get that mean, that sample mean. All right, so we have 0.55 minus 0.3, so that gives us 0.25, and then, 0.55 plus 0.3, I just did minus again, plus, okay, 0.85. So we can be 95% sure or confident that the mean is somewhere between 0.25 and 0.85. Okay. Again, we can be 95% sure that our actual population mean is between 0.25 and 0.85. Okay. And then we're not going to do the are you ready for more, but you can take a look at the summary if you want.